All right, our next speaker is from Iowa State. Antonio Mallarino is a professor of agronomy, nutrient management research and extension specialist at Iowa State University. His research and outreach efforts have focused on cost-effective, sustainable, and environmentally sound nutrient management practices for Iowa cropping systems. He's had an extremely highly productive career at Iowa State, which started in 1993. So welcome, Antonio.
Thank you so much. Actually, I wish I could be there in person. But I'm sorry, but really I cannot make it so far north. And then tomorrow we have meetings here in Iowa. I was saying that it's obvious that Dave Franzen worked a lot in Illinois with Ted Peck, which was one of my great mentors. And I believe he is the one that knew more about soil testing and mineralogy and all these things. Of course, each of us, Dave Franzen, Dan Kaiser, and I have our own research and our own sometimes different soils. Other soils are similar, especially southern Minnesota and northern Iowa. But we have different experiences, different research, different perspectives. So I'm hoping this would be useful for you guys. I'm not sure how many people from Iowa are listening to this. So I will kind of talk, mainly from Minnesota and North Dakota. Okay, here it goes. There are a few things, about soil testing that we have known for more than 100 years, maybe more. Several soil test methods for a nutrient exist all over the world. Phosphorus, for example, there must be about 20 different methods. Potassium, there are probably 2, 3, or 4. Some methods are more appropriate than others for soils with contrastingly different properties. This is it's difficult to define. You see, two soil series may have different names, but they can be very similar in relevant properties for us, but others might be very different. So a soil test result is meaningless without field calibration with crop yield response. Dave Franzen showed that very well. So we need to develop interpretations for different soils, crops, and tiller systems, sampling times and depths, and then some lab handling methods. Now, people talk about field correlation, field calibration, and often can be kind of confusing. You see, field correlation relate test values to crops response across many site years. So the main thing there is to find the critical concentration or range. I mean define where soil test values above which seldom there is response and below which there is a response. We need to find yield or relative yield for the efficient values and establish interpretation categories or equations. And for these treatments can be just a control and one non-limiting but not excessive rate. Now, field calibration per se goes beyond that. And the main objective is to find the application rate needed for a range of the efficient values. And for this, we need more complex, expensive trials with several application rates. Now, soil testing is problematic. There is more uncertainty for soil testing and prediction of crop response than for P or pH, for example, at least in Iowa. There is much higher temporal and spatial variability, complex reaction between the soil scale pools, some of them they talked about, moisture issues in the field or in the laboratory, the potassium recycling from residues and rainfall, especially in the fall and before planting in the spring. And then we have all these kinds of induced K deficiency that we can see deficient symptoms even with high soil K levels sometimes. And then, this is due to dry, wet, compacted, or loose soil. And then sometimes also root damage by diseases or insects. So all these factors affect in different ways the soil test correlation and calibration, as well as the K fertilizer management. Now, I'm not a soil chemist. I'm a soil fertility researcher extension with mighty boots, or at least I used to. So I like to show this scheme, of course, soil chemists have a heart attack when they see this oversimplification, but I believe is useful. These are the three main pools, that we have in the soil. The yellow on the left is this potassium solution that always is very small. Then we have the exchangeable K, and then we have what I call not in readily exchangeable K forms. Some people call it non-exchangeable K or fixed K, which in my opinion, those are some of the worst names soil fertility and soil chemistry researchers have used, in the history of soil fertility research. The routine soil K test measure the K ion solution and the exchangeable K, okay, that orange block. Now, some of the so-called non-exchangeable K, which as I said, I hate that name because it's not so, becomes exchangeable over time, even during the year, much faster than most believe, but its measurement is very expensive and tedious. And I have had three students, one from Argentina, Matt Clover, Ryan Olmans, he's from Minnesota and working with me, his PhD. And we are very frustrated, but I'm not gonna talk about it. We are still working on that. So many factors influence the amount of K measured by soil tests across different soils, but mainly are the clay type, the soil hydrological regime, and the sample drying temperature in the lab. So in the North Central region has been an incredible amount of research over times, but mainly during the 60s, I would say, in most states of the North Central region, a 6-inch sampling there was adapted, except for Illinois, they're still sampling 8 inches. What the soil drying temperature was standardized for the labs because these affect the potassium that is measured. The soil clay mineralogy at the time either was not studied well or was not relevant, so was not used. The cation exchange capacity or percent K saturation, it was obvious that it wasn't useful or was not used. Again, with some exception, for example, Ohio, that until recently, they have three different interpretations based on different CC. They changed it recently only to two, that they have essentially beach sand soils and then all the rest. But most states adjusted the K interpretations from soil testing for different soils based on texture, subsoil properties, or the subsoil potassium level. The testing of field moist or slurry samples was studied a lot from especially Iowa, Illinois, Indiana. And it was clear with field trials and greenhouse trials that the not drying the soil sample was a better predictor of the crop response, but its value tended to decrease from West Central Iowa to Ohio for some reason. And since then, there has been a dry and a moist test procedure included in the NCR 13 committee methods book. Now, in Iowa has been a long story of potassium testing, and I will not go in detail, don't worry about it. But in the 60s, began using different K rates or soil test K interpretations for soil series with low or high subsoil potassium levels. Another thing was that field research showed large benefit of the moist sample handling procedure and no difference for the P test. It doesn't matter if you dry or not the sample. So the moist or slurry sample handle procedure for P and K was implemented by the Iowa State University soil testing lab from 1963 to 1987. In '88, I was still a student here in my last year of the PhD. The moist test was dropped because private labs didn't adopt it, and the excuse was complicated handling procedures. So at the time, Iowa State used a factor to transform the interpretation they had based on the moist test to the dry test. I wish I had been working already as a professor or a postdoc at the time, but I wasn't. Then in 1996, I started in fall of 93. And my postdoc, I did lots of research with P&K. In 1996 and 2002, we increased the recommended test values that they had in 1988 based on research. So I have lots of graphs, sorry, but I just want you to just take a look at the big things. On the right, we have a corn yield response, relative corn yield response, and on the left, and on the right, we have soybean. So I put here in black and white for both the soil series that often have a higher potassium need, at least as indicated by the soil test, be the ammonium acetate or the MELIC 3. As you can see, there is these black dots fit in completely different ways, and you can see the tremendous variability that there was, at least at the time, for case testing. I wasn't too sure this was due to the soil texture, the mineralogy at the time, or the subsoil properties. But based on that bad correlations, you see, look at the soybean correlation. Essentially, the potassium test is crap. It's just good to say if you have enough or have a deficiency. There's no way you can fine tune, the potassium management with that. So I decided, hey, we need to work on this moist test again. So in 2001 to 2006, we worked on 362 site years across 32 Iowa soil series with corn and soybean. We tested the samples by the dry test and the moist or slurry test. You get the same thing, either with a field moist or preparing a slurry, with little modification from the old version for both the ammonium acid and MELIC 3. We also studied a bit the drying temperature effects for selected soil types. And then we found that the moist test was as good as the old research showed for many soils, but especially with soils with drainage somewhat poor to very poor, highly productive soils. For example, those in the Des Moines Low, southern Minnesota, central, northern Iowa, things like that. We also work on the K reversion by pre-treating already dry soil samples. Brian Hill, my master student, worked on that, but it wasn't nearly as good as the actual moist test. So this is why we have my student, Pedro Barbagelada from Argentina, did it in 2002, 2003. So what we have here in the y-axis is the extracted potassium increased over the field moist test, okay? So the moist test does not hit, does not anything with the soil. And then we have 3 air temperatures, air dried, 40 degrees C and 50 C. The temperature that has been standards in the 60s is from drying temperature is 35 to 40 degrees C. So these are different soils that we selected based mainly on the drainage. So some, you don't have a clue what they are, but for example, Clarion, Canyon, Pringer, and Western Canisteo are common in southern Minnesota and northern Iowa. So you see that the biggest thing is that different soils have a tremendous difference in the difference in the potassium measurement when the sample is analyzed just moist or is dry. and then the higher the drying temperature, here we did a 50 degrees, which is the black bars, then we have the highest difference. It's huge. So if you look at the blue letters, this here with little change are well drained or moderately well drained. Okay, then we have some intermediate soils, and then when we get to the poorly drained or the somewhat poorly drained or poorly drained, then we have this huge difference. Now, back in 2003, Dan Kaiser wasn't there yet, I think. So Roger Eliasson and George Ream did some work for the NCR 13 committee at the time. Dan may have these. I just want to show it because what they did was use in two soils. I don't have a clue what the Copaston sandy loam is, but I do know the Canisteo, common in southern Minnesota and northern Iowa. And they, so two soils, and then they dried, at different temperatures, not dried or field capacity, moist and so forth. And then they also extracted with 4 solutions, the ammonium acetate, which was at the time the most used, the Melic 3, which now is the most used for P or K, and then barium acetate and magnesium acetate. And as you can see in this sandy loam, there is not much impact of the drying or not on the extractants, and seems that these two, the ammonium acetate Melic 3 extracts more, and the calibrations are being done for those. But then in this silty clay loam, poorly drained Canisteo, they found exactly the same thing that we found in Iowa, and this happened for the 4 different extractants. So what we did from 2001 to 2006, we went back to the field, and we did lots of field response trials. So what we are showing here is for corn, okay? Corn on the left for the dry soil test K, the commonly used, and here on the right, the moist test. I don't need to be a PhD to see that the dry test have many different values, for different soils for a similar potassium level. But in the moist test, it's not as good as the phosphorus correlations are. But we see that most of the soils are now in the same curve. So a test difference make a big difference with the dry test, but not as much for the moist test. So this is good, because then that means that we don't need to have different soil test interpretation, okay? And as you can see here, the black dots is the soils that are have poorly drainage, very, very productive, like the Webster, the Canisteos, the Colo, Judson, all the Harps, all the soils. But you see, essentially, there is absolutely no correlation with the yield. You can have a response, of 150 bushels to nothing within about 120 or 150 parts per million. Here is almost kind of a vertical distribution, but the points are more tied together, okay? This is soybean. For some reason, the dry test is worse for soybean here on the left than for corn, and but the calibrations curve for the moist test are about the same than for corn. So now people, since we started working there, especially people from labs, tell me, Antonio, can we just have a correlation factor, a correction factor, that we can say, okay, with the dry test is this, with the moist is that. See, that labs love these factors. They keep using them, often I'm not sure we had basis. But here you see on the left that, it's impossible. There is no linear relationship. Depending on the soils, the dried moist K ratio changes, and when we have soil test value by the moist around 200 parts per million or higher, There is no difference between the two tests. It's about the same. And I do have data now that in some soils, actually the moist test extracts more K than the dry. But still, the correlations are better for the moist than for the dry. Here we study the effect of the soil sample moisture contents, and yeah, there is a positive correlation, but it's all over the place. So this result did not surprise our soil chemists here. World soil chemists have demonstrated in many lab studies since the late 50s that for high charge and expansive smectite and vermiculite clay minerals, Dave Franzen explained very well what those are. Alternating dry and saturated lab conditions often alters the K retention release process. They have been saying that this likely happens through aeration, changing some of the iron in the clays to reduce or oxidize forms alternatively. So, and this changed the spacing between those clay layers that they talk about and the strength of the potassium retention there. This also happens when soil samples containing high proportion of these clays are analyzed without drying or by drying them at different temperatures. So this could have been expected in some way. So based on this research, we did more additional, more trials in 2011, 2012, mainly by Matt Clover and Ryan Oldmans. And so the new soil sample handling chapter in the NCR 13 methods now include the moist test. It was there in the 60s, then it was dropped in the 80s, and now we put it back again. We prepared a chapter with Ron Gelderman from South Dakota, now retired, and I. So at the same time in 2013, Iowa State lab update, Iowa State Extension updated interpretation for the dry test, again recommending higher levels than before. It seems that since I started working, I have been pushing up the suggested potassium levels 2-3 times. And actually now, a new recommendation coming next week, it goes even higher. And at the same time, introduced the moist test interpretation. And the Iowa State Soil Testing Lab began offering both tests. So at the same time, a new private lab opened in Iowa, Solon, using the slurry sample handling procedure as a default. It was doing well until Monsanto bought it. And then after 1 year and a half, they saw that they were not making money and they closed it anyway. But soon after Solon started and the Iowa State lab, Axor's lab, mainly in the branch here in Iowa, in Ellsworth, began offering the moist test. And then a couple of other labs operating in Iowa followed. Okay, so these are the new correlations. Of course, we have many more sites, but these are essentially on the left, the dry test, the moist test, and we have corn and soybean. They follow about the same relationship there. And we see again, this more tight response with the moist states where there's much less difference between the different soil types than with the dry test. So these were recommendations that we had in 2013, and we're not going in detail, but I showed this because here we have our interpretation classes, which are current up to now, and then we have the dry test for the ammonium acid or the MELIC3, which is the same, and then we have interpretation for the moist or slurry test version. And these are the fertilizer recommendations, okay, for the 5 interpretation class. Now, I work a lot with the economics of fertilization in relation to soil test level. This is something that I did in 2015. We have 3 scenarios. I kept the price of the potassium the same. Sorry, here on the right says 0.55, but actually it's 0.35, okay? And then this is good crop prices, intermediate, and horrible. And as you can see, really, this is the dry test. This is crap. this test, essentially the only thing it's good for is to tell me when I have extremely low K and then a response is very likely, and when I have too much and the response is unlikely. But if somebody wants to fine tune, we have this huge blob into in the ranges of most interest. It doesn't matter what is the price level. Now, this is for the moist test, you see, and here I got right the prices for K2O, pound of K2O. And as you can see, at least here, you can make better decisions. You can have, okay, low and very low, a high probability response. In the optimum, you toss a coin, it's about zero, the expected return, and then in the high testing soil, there is nothing. So that's why we have been pushing for this test. Now, the view of Iowa soil clay mineralogy have changed a lot over time in Iowa. So you need to remember that the clay mineralogy used for the soil classification by the USDA is from a subsoil layer. It's not, does not apply to the surface soil layer, which is normally tested. Sometimes it's the same, often it's not. Now, we couldn't analyze clay mineralogy for all those sites that I just mentioned. But the word here in Iowa, I was told by the soil chemists that Iowa soils are dominated by smectites, 60 to 70%, mostly montmorillonite. There are 3-4 different kinds of smectites, with much less illite, about 20%, kaolinite, 10 to 50%, and vermicular very low, 0 to 5%. However, in 2015, we finally got to work on mineralogy and look at and we saw that there is much larger variation in this mineralogy. So the first thing we did, this is the graph that I showed before that we did in 2003, and I added these pie charts on the top with the mineralogy. And as you can see, it's not very clear really that the mineralogy has something to do with these differences between in potassium extracted with different temperatures. The most have dominant smectite, and the only kind of clear thing is that here in the western Canisteo soils, poorly drained from the Des Moines low, the smectite is much more dominant than in all the others. So now, then we did much more research. So we did about 250 plus field trials since 2013, using several treatments. We used the melic and the ammonium acetate, dry and moist, and so forth. But we also studied clay mineralogy and potassium retention capacity in some selected soils from Iowa and a few from Illinois, Indiana, Minnesota, North Dakota, and Wisconsin. I'm not showing the data for these other states, and I already gave people the results. These are the calibration, and this is on the left is the dry test, and on the right is the moist test. It's exactly the same thing that we were getting since the mid-90s, exactly the same, you see. And now we have much more data. This is new trial since 2013. Then this here is the same thing, but I put the different points based on the drainage. The black are the poorly drained soils that the Canisteo, the Websters, or all those harps, or Koboshes, all that stuff, and Colo. And then as you can see, with the dry test, all these points are around here. There is no way that even a specific interpretation or calibration for these soils will work. However, in the moist test, they are all aligned in the same curve. So with the moist test, we don't have problem. We use the moist test, and then a certain test results means the same thing. It doesn't matter what the heck the soil is. This is much better than that, than the dry test. Now, I know this is complicated, and I'm not sure what time it is, but I try to show what is different in the soil for three groups, trying to simplify, which are these same groups that I put here, the good, moderate, poor. Okay, the dry test versus the moist test ratio. okay? Yes, it's a bit higher in the poorly drained soils, okay? And not much difference with the other. So the black is the poor, the red is the moderate drainage, and the well drain is the green. Okay, organic matter. We have a bit higher organic matter. This is the problem out there. Many things change across contrasting soils. It's not just one thing that changes. Soil clay, texture, not really a difference. It doesn't make any difference. The CEC, not much different, but seems that those soils with poor drainage have a bit higher CEC than the others. But look at that. It's mainly a 3, 4, 5%, and that's well within the error, you know, when we analyze for those things in the lab. Now here below on the left is the smectite in clay, the percent. And you look at the black bars, it's clear that the dominance of the smectite is a bit higher in the poorly drained soils than in the other two. Now we look at the highlight proportion, or mica, some people call it, in the soil clay. And then we see that in this poorly drained soil, we have about 10, 12%. We have in the other, with better drained soils, you know, we have about 20, 22%. And then we look at kaolinite, which by the way is more than some people said before, and it's just about the same, no difference. And this is the K rotation index. I'm not going to explain what it is, but it's a lab quick test that supposedly is related to how the soil retains or release potassium. Okay, so but it doesn't really relate well with field and long-term trials. We have that, and it doesn't. It's very misleading. But anyway, we can see that in the poorly drained soils, there is some rotation. The higher numbers means that when we do the test, there is some potassium retention. But for the other two classes, there is a release actually. Of course, we use a concentration, you know, shake with the soils and analyze and so forth. So it's not just one thing that changes. We have, yes, the drainage is the main thing, but we have a bit more organic matter. We have a bit more CEC. We have a bit more smectite dominance and less highlight, you know, in some of those soils. So now, I'm sorry, I know this is complicated, but what I try to do that is to simplify and have groups of soils and the different soil clay types. So on the left, we have 3 groups here with a smectite highlight ratio, 6.1, very high. That means that we have about 60% of the clay is smectite, 2.3 and 1.2. And then we have here, the smectite is the black, the highlight is the green, the gray is, dark gray is kaolinite, and the light gray is vermiculite. So, of course, when we have smectite dominant, see, we can see that clearly, but also it's important that the highlight proportion is very low. It's about 10% on average. And really, the kaolinite and the vermiculite don't change much, you know. Now, here on the right, we have the groups according to drainage. That's what we have, you know, for the moist test. We say that the moist test works better, much better than the dry in soils with moderate or very poor drainage. So here in the very poor, I mean, we see clearly smectite, the black bar dominant, again, small proportion of highlight, and then for the moderate and moderately drained and well drained, there is not really much difference. Now, if you look at this, and as I said, I know it's complicated, you look at these 2 graphs, the one in the left and the one in the right, they're about the same. So really, the drainage is the much easier thing to use, and clearly the moist test works better there. So why we're gonna bother here with the clay type? So what do we think? The data analysis continues. Ryan Olmans, he's from southern Minnesota, has been working on this for 7 years, from his master's and the PhD. Most Iowa soils have mixed clay mineralogy with smectite dominant, with few exceptions. And vermiculite that behaves like smectite concerning K is very low and about the same 5 to 8% across soils. Few soils have about equal proportion of smectite, alite, and kaolinite. We think that the soil hydrologic regime is the main cause for the moist test being much better in soils with a bit poor or very poor drain. We believe this is the most important thing and the easiest to identify. But we recognize that they also have slightly higher smectite, slightly higher CC, and slightly higher organic matter. So in our view, the moist test is the most practical tool to minimize differences in soil test K interpretation among Iowa soils, because that's when we have this clear difference. And a special calibration of the dry test for those soils does not work. It's useless. It's a waste of time. We need to use the moist test. Therefore, based on all this, we are not considering clay mineralogy for the updated potassium recommendations that are coming next week for Iowa. And I discussed this with Dan Kaiser a lot. Okay, this is again our new data set. In the top, we have the current interpretation categories in red, and in the bottom in blue, we have the new categories that become effective next week. As you know, the main thing was that we make the optimum class, for which we recommend removal-based maintenance, is much wider and went up a little bit. But look at the color of the points. The white is medium smectite, medium mica, medium kaolinite. The gray is high smectite, medium mica, medium kaolinite. And the black are these dominant smectite with very low mica and medium kaolinite. And this is for the moist test. Okay? The chart in the right, in my view, is horrible. You cannot fine-tune potassium management with this dry test, at least in Iowa. In the right, we have the moist test, which is better. Now, here is exactly the same thing, but now we have the drainage classes. The white are the good drainage, the gray is the moderate drainage, and the black is the poor. So, if we have this, and we have already implemented the soil test, why in the world we're gonna mess up with the clay mineralogy when essentially we see the same thing? And as I said, using the moist test, is the most practical thing. So that's what we believe. Now, frustration with potassium testing are very old and continue. I remember Ted Peck, he was the soil test for K super guru from Illinois. I think that was the best in the United States or the world, who retired and passed away years ago and was one of my many mentors. The last time I talked to him, he was already retiring. And I was, as always, asking questions about soil K, and everything I asked and I thought was a great idea, he said, oh, we did that in the 50s and the 60s, blah, blah. So he told me, Antonio, I work on potassium and its capricious nature for more than 40 years, and I'm retiring frustrated. Good luck to you. This was 35 years ago. Prophetic words. I'm in the same boat right now. I'm thinking of retiring later this year. And yes, we learn a lot about potassium, but still, it's really a pain in the neck to work with potassium. I don't know, hopefully there are some time for questions. And I'm not sure how is that we'll be handling the questions. Somebody told me, but I forgot. So should I look at the chat, or somebody will tell me what the questions are? So thank you. Okay. Seems that here, I see the question. Great, this is good. On the moist slurry test you discussed, is water used as the extractant? No, no, no. There are two ways. In soils that have, say, more than 40% clay, doing the field moist actual test is a pain. So we do a slurry with water, a certain ratio, okay? That's water where it's used. But then we use either the ammonium acetate or the melic-3 extractant, and both tests behave the same for dry or the moist test. Do you think it's just the clay, or is there an effect of organic matter in the poorly drained soils that affect that? Well, that's what I showed that. I think it's the hydrologic regime in the field. Those poorly drained soils, which are highly productive, although sometimes, you know, when it's too much rainfall, you don't get any corn or soybean. I think that these changes in the field, from saturated conditions to very dry and so forth, that screw up those clay interlayers that Dave was talking about. So I'm not sure if it is organic matter. I think it's the hydrology mainly, the changes in the field, because that coincides with the large changes or not when somebody dries the lab in the samples in the lab. But it could be, as I said, a bit higher SMECTA dominance, a bit higher CEC, and I don't know why, honestly, why higher organic matter. I don't think the higher organic matter explains much. The other question is, oops, I lost it. Oh, there it is. What about the soil in Iowa have layer cities that are transitioning between SMECTA and vermiculite with proper intermediate? Likely, but you know, this is something that you need to understand that the clay mineralogy analysis is much more a qualitative thing than not quantitative. There is huge variation, so we can fine tune. And actually in Iowa, we did the X-ray, which is the most common, but then Dr. Thompson, the soil chemist, used this thermal analysis. And our interpretation of the clay type was based on both the X-ray and the thermal analysis. And yes, there may be some kind of intergrades. And actually, there are a couple of people here that we're studying how long-term potassium management may change partially the clay mineralogy. See, we have experiments with from 30 to 42 years without any K or with different K rates. And now somebody's looking into that because we may have all kind of these clay changes over there. Any recent case of microbes in the soil to provide another layer of content of area K? I don't think so. I don't think so. You see, the reaction in potassium in the soil, it's mostly physical-chemical reactions, you know. I don't think that the soil microorganisms play a major role, but it could be. Clearly there is an impact on nitrogen and sometimes on phosphorus, you know, but I don't think that in potassium that would be a thing. But as I said, most of us working in potassium are frustrated. Every rock that we turn, we found a scorpion below, and seems that we get more questions than answers over time. Okay, I believe my time is over, isn't it? So thank you so much.